This conference will now be recorded.
Very good evening, students. Today we'll be discussing few numerical problems based on JEE Mains, JEE Advanced NEET paper from this topic, kinetic theory of gases, and then we'll conclude this chapter. So you can see the questions in the screen. I'll read out and I'll discuss. I'll tell you the tricks how to solve these problems, etc. So the first question is, says that if gamma be the ratio of specific heats of a perfect gas, the number of degrees of freedom of a molecule of a gas is 25 by 2 whole into gamma minus 1, or 9 by 2 whole into gamma minus 1, or 3 gamma minus 1 divided by 2 gamma minus 1, or 2 divided by gamma minus 1. So which one out of these four options will be the correct answer? That you have to find out. Good evening, Guna madam. Are you able to hear me? Okay, kindly message me if you are not hearing. Then I have to check my network. So you know this gamma is the ratio of specific heat. That is Cp by Cv is equal to gamma. Okay. Neither Cp nor Cv is given. So you have to find out this gamma in terms of degrees of freedom. Okay. You have to find out a relationship between gamma and degrees of freedom F. Actually, you have to find out the number of degrees of freedom of a molecule. If the specific heat, ratio of specific heat gamma is given. So do you know the relation between degrees of freedom and specific heat? The ratio of the specific heats gamma. Okay, if not, please note down this. Degrees of freedom, the gamma is equal to 1 plus 2 by F, where F is degrees of freedom. Degrees of freedom. So this is a relationship between gamma and degrees of freedom. Okay. So from here, it is easy to find out what is degrees of freedom for the given gas, for the molecule of a given gas. Okay, so if we solve for F, look, this will go gamma minus 1 is equal to 2 by F, and F will be 2 by gamma minus 1. So this is the answer. You have to find out whether you have that option. Yes. So this D, option D will be the correct answer for this question. Okay. So you have to remember the formula gamma is equal to 1 plus 2y F, where F is the degrees of freedom. So this is the key point here. Now, here an ideal gas, in the second question we see an ideal gas is expanding such that Pt square is equal to constant. Okay. So you have to find out the expansion, coefficient of expansion of gas. Here it is, I guess. This should be is. So you have to find out the coefficient of expansion of gas. I think it is the coefficient of expansion of volume expansion. I hope this is the volume expansion. So coefficient of volume expansion. Okay, volume expansion. So coefficient of expansion of volume is also denoted by gamma, right? Alpha, beta, and gamma. You remember, this is related to length, this is related to the area, this is related to the volume. Okay. So anyway, so gamma is defined as dV by dt whole into 1 by v. Okay. So this is what you have to find out. So 1 by v into dV by dt. Okay, so this is the volume expansion coefficient. So to find out this dV by dt into whole into 1 by v, look here, this is for an ideal gas. This is for an ideal gas. So what is given is Pt square is equal to constant. Let us write that constant as c. Okay, then actually we should have an expression with v, right? So we know that for suppose 1 mole ideal gas, PV is equal to RT, right? So from here, if we replace the P, what we get? P is equal to RT by V. So if we replace P, suppose this is equation number 1, this is equation number 2. So replace P in equation number 1. Okay. So if we replace that, RT by V into T square is equal to constant. So this would give you V is equal to R T cube by C. C is a constant, we don't mind. Okay, let us remove this part, we don't require now. This is what we have got now. V is equal to, we have got this. Now what we have to do? We have to find out gamma. That means, see, when we have got V is equal to RTQ divided by C, we can just take the derivative of, okay, so I did not mention this. V is the volume, this is the temperature, absolute temperature. So here T is the absolute temperature. So this is a function of temperature. I can take derivative dV dt, which will give you 3R T square divided by C. Okay. Now we have got dV by dt. We know what is V. So if we just put these values, suppose this is 3 and this is equation 4. If we put this in equation this 5, suppose this is equation 5. Let me just erase this portion what was given earlier, and let me erase this part also. Okay, so we'll write these values now. Okay, so dV by dt is 3R T square divided by C. And what about 1 by V? 1 by V will be C by R T cube. Okay, so look here, CC will be getting rid of C and C. So you will get actually 3 by T. Okay, so this is the answer. So this is the answer. Okay, so you have to read the question carefully, and then you have to understand what has been asked to do in this problem. So here the problem was given that an ideal gas is expanding in such a way that the equation of state can be expressed as Pt square is equal to constant. Now you have been asked to find out the coefficient of volume expansion of the gas. Okay, so you need to know the definition of volume expansion of the gas such that you can solve the problem. So this is the key point. You have to remember what is volume expansion coefficient, 1 over V whole into dV, sorry, dV by dt. So this is the key point over here. You need to know the definition, dV by dt, and you have to remember that this is ideal gas. You can anytime write PV is equal to RT. This equation of state you can use anytime, okay, for an ideal gas. So if we replace P from here in the given equation, then we'll get a relationship between V and T. From there we can find out dV by dt, and V also will be finding out from here itself if we replace P. So that's how we have solved this problem. So 3 by T. So the answer third, option C, is the correct answer for this question. Okay, so you have to remember this key point. Now, the mean kinetic energy of 1 mole gas per degree of freedom on the basis of kinetic theory of gases is. So this is actually the statement of, if you remember the statement of equipartition of energy. Equipartition of energy, then you can solve this problem. Okay, you can find out the answer for this. See, equipartition of energy, statement of equipartition of energy was that the mean kinetic energy, if I write ek, mean kinetic energy will be given by, okay, so the mean kinetic energy is given by the, or in other words, each degree of freedom, or per degree of freedom, here this is, so energy shared by per degrees of freedom per molecule, per degree of freedom per molecule is half kT. Per degrees of freedom per molecule, per degrees of freedom, per degree of freedom, per molecule is half kT. But here you have been given 1 mole gas. So 1 mole gas means you have already n Avogadro number of molecules. So Na into Na has to be multiplied with this. So you get Na and K is actually R, the universal gas constant. So you get half RT. I hope you understand this. So I hope this is clear to you. You have to remember the correct statement of the equipartition of energy. Each degree of freedom per molecule. We had said each degree of freedom per molecule is half. So the average kinetic energy per degree of freedom per molecule is half kT. When we talk about mean kinetic energy of 1 mole gas per degree of freedom, for 1 mole gas, then the Avogadro number comes over here, and Na into K, K is the Boltzmann's constant. So this two combines to give the universal gas constant R. So the answer will be half RT, not half KT. See, you might be confused. Half KT, it is not the answer. You have to remember this will be half RT because because here it is 1 mole gas. Kinetic energy, mean kinetic energy of 1 mole gas has been asked per degree of freedom, not for a molecule. If for a molecule, then half kT. So this is what I need to say over here. Now, so we have solved how many? Two questions we have already solved. Third questions also we have solved. Now come to an important question. This is very important question. Fourth one. A gas mixture consists of 2 moles of oxygen gas and 4 moles of argon gas. Okay, 4 moles of argon gas at temperature T. Neglecting all the vibrational modes, total internal energy of the system is. Okay, so you have to neglect the vibrational modes. So how to find out that internal energy, total internal energy? So there is a mixture. So there is a mixture of gas. One is diatomic, another gas is monoatomic gas. Okay, one gas is diatomic, another one is monoatomic gas, right? So oxygen is diatomic gas and argon is monoatomic gas. So there are two different types of gas. They are mixed to get a gas mixture at temperature T. So you have to neglect the vibrational modes and then find out what is the internal energy of the system. So internal energy is actually directly related to temperature, and mean kinetic energy is also directly proportional to total internal energy. So mean kinetic energy is also directly proportional to temperature. So we can use the equipartition theorem to find out the total internal energy. So this is, see, just few minutes back we have solved the problem that half kT, but if it is a mole, then you have to multiply the mole. Okay, for 1 mole it is a half RT that we have seen. So if there are 2 moles, 3 moles, 4 moles, you have to multiply this, and obviously you have to multiply the number of degrees of freedom also. Okay, so let us find out first the internal energy. Here you have to find out total internal energy. U is actually for U for oxygen and U for argon. Both you have to find out. So this and this can be found out separately. Suppose internal energy for oxygen, it is a diatomic gas. See, diatomic gas, how many degrees of freedom should be there? Okay, see, this is, there are two, so we know F is equal to 2n minus, sorry, 3n means here 2 minus L is 1, so you get 5 degrees of freedom. Okay, so 5 degrees of freedom is here. So 5 degrees of freedom means you get 5 per mole for 1 mole. 5 by 2 RT, 5 into half RT for 1 mole. But how much, like how many moles are there here? 2 2 moles of oxygen is there. So you get 5 RT for this oxygen. So this is the internal energy for due to oxygen. And what about internal energy due to argon? We have to find out. So this will be, so here also you have to find out for monoatomic gas what is the degrees of freedom. Degrees of freedom will be, see, n is equal to 1 here minus 0. So you get 3 degrees of freedom. So if you have 3 degrees of freedom, then see here you argon will be, see how many moles are there? 4 moles. 4 moles half into RT into number of degrees of freedom 3. So you get 6 RT here. So if we just add this to how much we get, 5 RT plus 6 RT, and this will give rise to 11 RT. Okay, the total internal energy of the system is 11 RT, and the answer is here C. See, whenever there is a gas mixture, you have to find out the internal energy for the component gas separately. Component gases separately. Here, the component gases are 2 moles of oxygen, which is a diatomic gas. So 2 moles means 2 into degrees of freedom is 5 into half RT. So that is what is the internal energy for 2 moles of oxygen gas. And see here 4 moles, that means 4 into half RT into the degrees of freedom, that is 3 over here for a monoatomic gas. So we get 6 RT. So that's how we get the total internal energy by adding these two internal energies of the 2 component gases. Okay, so this is an important question, and JEE Advanced or JEE Mains, or there is a finite probability to come in NEET UG exam also. Now we'll solve the 5th problem. So this problem is asked in 2015 JEE Mains. Okay, so JEE Mains, JEE Main 2017 question. Okay, sorry, 2015. I'll read out the problem and try to solve it. So consider a spherical cell of radius r. Spherical cell means you have a sphere like this, and you have, actually you have two hollow sphere, and in this region it is called cell, spherical cell, spherical cell. Okay, this is the spherical cell, and it has a radius from here, some radius r. I'm sorry, this radius, okay, this has a radius r, and the black body radiation inside this cell means you have a first container, you have second container, and in between the space is called actually spherical cell. So in that empty spaces, suppose you have black body radiation in terms of photons. Sometimes the photons, even phonon also considered as, at least the photons are considered, this is very well considered as, photons are considered as ideal gas. photons are considered as ideal gas. Ideal gas. If photons are considered as ideal gas, then we can actually write down for photons also PV is equal to nRT for n mole photons. Okay. So these are the things like ideal gas means ideal gas equation can be applied. That's what I wanted to mean. So here the internal energy per unit volume, which is this capital U by total internal energy divided by total volume. So which will be the density of volume density of internal energy, total internal energy, and that is varying as T to the power 4. So density, energy density, internal energy density varying as T to the power 4. So this is one parameter which we have got. Another parameter is the pressure the photons exert on the wall of the spherical cell is given as 1/3 U by V. U by V. So these are the two informations given. Now you have to find out if the cell now undergoes an adiabatic expansion, what will be the relation between T and R? This T and R. What will be the relation between T and R? So how to solve this? I'll just remove this part so that I can get some space to solve over here. Okay, let me just take a boundary over here. Let me erase this also. So we have to consider the photons of black body radiation as an ideal gas. Ideal gas with internal energy is given as internal energy density is given as U is equal to U is directly proportional to T to the power 4. So this can be see. So this can be written like this. K is a constant T to the power 4. Okay, now look, if I write P is equal to the given term 1/3 U by V. So U by K 4. Okay, we have to find out the relation between R. Okay, where the radius of the spherical cell small r is given. Okay, so this we have to bring into the picture. So how to do that? So we know for an ideal gas PV is equal to RT for say let us say 1 mole of photons are there. So I'm writing RT. So from here we can get V is equal to RT by P. So this you will get easily, right? So if we, I'm sorry, we would have done the opposite. We'll replace the P over here. Okay, we'll replace the P. P means RT by V. I can write. So let us write RT by V. RT by V is equal to 1/3 K T to the power. This K is actually a constant, not Boltzmann's constant. You should remember this. So from here, you look, this will be 3, and if I write V, and V will be equal to divided by K T. So this is get relation between V and temperature to be T to the power V T to the power minus 3 from this equation. So what we have got, I'll write over here. So we have got V is equal to, look, this V is equal to 3R divided by K into T to the power 3. Look, this is a constant term. This is not the Boltzmann's constant. Otherwise, there will be some simplification done with this R. This is a constant term, constant Boltzmann's constant. Okay. So this can be seen as this. You can see. So you have to find out the relation between B and T. You look, we know for 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 a sphere, V is 4 by 3 pi r cube, right? Okay, r cube. So in this, actually, this implies V is directly proportional to the power minus 3. From here, we can say V is directly proportional to r to the power 3. Okay, so this is what we have got. From these two, actually, we can write something. We can write the 3, r to the power 3 can be written as this. Okay, or we can write is directly proportional to or minus 1, or in either way we can write T is directly proportional to 1 by R. So this is what we write. Okay, so there is a relationship between T, temperature, and the radius of the cell, temperature and the radius of the spherical cell. Okay, so it was, so this answer is the correct answer for this case. So this was the fifth question. I hope you have understood. So these are the terms you should be using for solving this problem. C, U by V is directly proportional to T to the power 4, and P is directly proportional to or equal to 1/3 U by V. So in place of U by V, we have written K into T to the power. So U by V, you can write 3 K is proportional to constant T to the power 4. Then you can replace those. So since it is ideal case, we can write PV is equal to NRT or PV is equal to RT. From there, we can replace the P so that we can get a relationship between V and T. So we have got V and T, relationship between V and T from the given information, that is V is directly proportional to T to the power minus 3. And again, we know in terms of R is the radius of the cell. We know the volume of the cell is 4 by 3 pi r cube. So now from these two, we can write this r cube is directly proportional to T to the power minus 3. Now from here, we can simplify and get the relationship between temperature and the radius of the cell. Okay, so which is found to be T is directly proportional to 1 by R. Okay, so with this we'll stop this class for today, and we are done with this chapter. We have solved few important numerical problems also. These are actually just to give you hint or give you some idea how to solve problems, or to give some idea what kind of questions come in various competitive exam. Okay, so these are the typical questions which I have solved here in this class. All are actually from the either mains or advanced question paper. So you can also try. There are quiz questions uploaded in our site. You can go over there and then get those if you like to solve few more problems on this chapter. Okay, so I'll stop it here for today. We'll meet again with the new chapter tomorrow. We'll be discussing the chapter oscillations tomorrow onwards. So bye for today.